So we're going to be spending a lot of time, actually just about the rest of the class, talking about functions that come from the solutions of differential equations. And a little bit of work in describing how these are kind of unified goes a long way. Because you realize that if you want to, you can come up with your own personal set of orthogonal functions if you'd like. So this is it's called Sturm-Liouville theory. We won't get too deep into it, but I just want to draw the analogy to stuff from linear algebra, which is really useful in figuring out kind of on a global scale what's going on with this stuff. So I think Joseph Liouville was a French mathematician, and kind of weirdly, so was this guy Sturm, Jacques-Charles François Sturm or something. But we covered this when we talked about Fourier series and Fourier transforms, is that there are multiple ways of representing vectors, certainly, and you pick the one that's the most useful for you. And you can, in a sense, think about Fourier series and Fourier transforms in the same way, is that I'm taking my function f, and let's just not think about it as f of x. Let's just think about it like a thing, like a function, space of functions. And this is representing it in the position basis, but we don't really have to do that. So we could represent a function as x, fy, fz, if that was useful for us, but we could also represent it in some different coordinate system, f1, f2, f3. Likewise, f could be represented as f of x, where the game is you tell me a position on the real line, I tell you the value of the function, or we could represent the function as f of k, its Fourier transform, where this is an integral over the entire real line of f of x, e to the I kx dx. Right. But these both have all of the information that you need to get the function back. So this would be the k-space and the x-space representations of these. If you were looking at a JPEG versus a GIF, that in some sense is what you're looking at, or JPEG versus bitmap. I don't know about GIFs. So you're looking at Fourier series information versus pixel by pixel information. So this is where we're at least in terms of conceptualizing different ways of looking at functions. And you might ask the following two questions. So is that it? In some sense, we have what I've been casually referring to, because I'm a quantum mechanic, as the position basis and the momentum basis. I mean, those sound like useful things for a physicist. Are there other bases? So anything else? And the second question is, how do I generate bases? It won't surprise you to realize that the answer to this is a resounding no, is that there are a whole bunch of different ways of doing this. And what I want to talk a little bit about, and we won't again get too far into it, I just want to present this as kind of a conceptual basis for understanding what we're going to do and why everything kind of smells the same. Differential equation, set of functions, orthogonality criterion, generating functions, things like that, whether it be the Laguerre polynomials or the Hermite polynomials or the Bessel functions, is how do I generate these? There is also a really nice analogy to finite dimensional stuff. So for finite dimensional stuff, you have two ways of generating bases. So you have kind of a Gramschmidt idea, and I'll go through the Gramschmidt procedure if you didn't get cheated from that in linear. And you have another way of doing it, which is as the solution of an eigenvalue equation. So just say for 3D vector spaces. So we can Gramschmidt, and I always forget how to spell, it's scratched out in my notes, Graham, I think. No. Schmidt. Sounds like a medical thing. The Gramschmidt Procedure. And the Gramschmidt Procedure starts with, because we're in 3D, we need 3 linearly independent vectors. And they don't have to be orthogonal, they don't have to be normalized, they just need to be linearly independent. So I have 3 vectors, and no individual vector can be made out of a combination of the other 2. So maybe they look like this: v1, v2, v3. And there's no way of making v1 out of a linear combination of 2 or 3. There's no way of making 2 out of a linear combination of 1 and 3. And the Gramschmidt procedure goes as follows. So we won't, write out the steps. I'll just kind of sketch it. Is I just pick one. And because I'm uncreative, I'm going to pick v1. So first I normalize that. And that's going to be my first basis vector. So that's e1. Easy enough. So after I have e1, now I need to figure out how to turn v2 and v3 into things that have 2 properties. They're perpendicular or orthogonal to e1, and they're also normalized, so they're of unit length. Unit length is easy. The perpendicular part is less so much easy. So essentially what I do is I realize that, the part of v2 that lies along e1 can be given by the dot product. Right? So that's the part of v2 that lies along e1. So that's v2 cosine of the angle in between them. And I want to get rid of that part. So what I want to do is I want to subtract off v2 cosine theta v2 from v2. And then I have the remainder, the part that does not project onto v2. This is the angle in between them. So I want to remove the part that lies along v2. I want to keep the leftover part. It's going to look a little bit different. It's going to be shifted. Maybe it looks, goes over here or something like that. And then after I have that, I just normalize it, divide it by its norm, and I get e2. And then likewise, if I want to get the basis vector that's generated by v3, I project off the part that falls along e2, I project off the part that falls along, project off the part that falls along e1, project off the part that falls along e2, and then I normalize it. So I get rid of the shadows on e1 and e2, and I leave it over. So that's the Gramschmidt procedure. And in some sense, somewhat laboriously, that's what we did with Fourier series. We wrote down sines and cosines, and then we said, look, we've written down some sines and cosines, and then we showed that they don't overlap, and then we picked a norm, so this root 2 over t, to figure out how to normalize them. So that's the Gramschmidt idea, is you just give me things that aren't linearly independent, and I work really hard sequentially to make a set of basis vectors. There's something easier. So the second way of getting a basis in a 3D vector space is solve an eigenvalue equation. So I've got a 3x3 matrix M, and I've got a V, and I've got a scalar lambda, V. So just writing this out, or at least kind of sketching it, so this would be M11, M33, and then M13. And then v1, v3. And lambda is just a number. So that's the eigenvalue equation. So it turns out that when you solve this, for a 3x3 matrix, you will get 3 possible answers. And if the 3 possible answers correspond to 3 different lambdas, and M satisfies some certain properties, what you'll end up doing is you'll generate a basis. So this is the idea that, I'll just give an example so you can see how this works. Full details in your linear algebra book. But let's say that somebody asked me to solve, and what you're solving for is the eigenvalues and eigenvectors of the matrix itself. So you're given the matrix. So let's say that I was asked to find the eigenvalues and eigenvectors of this M. And I can not stare at this, but I created this myself, so I know. These three rows are linearly independent. Okay. So it turns out this has eigenvectors, 3 of them, -2, -2, 4. And this thing has eigenvectors, so they correspond in row-wise. So the eigenvector that I'm about to write down, -1, 3, -1, corresponds to eigenvalue 2. +4. Okay, and you can pump this through and see that that is the case, right? So, yeah. So these are the eigenvalues, these are the eigenvectors. Well, so you can take the dot products in between these, and you can satisfy yourself with the knowledge that these actually are linearly independent. So it turns out that these actually do exactly what we need them to do. And all I have to do is normalize them. So if I normalize these, I'll just do it for this because it's like really easy. So if I divide this by √6, and then I can actually verify that this kind of works out. So dot producting these two things, so I got -7, -8, +8. This dot that is 0. So these are not just linearly independent, they're orthogonal. So in fact, we kind of get this for free. All we have to do is normalize. So these, up to normalization, form basis. So for, you got to put some restrictions on the type of matrix. So this thing needs to have 3 linearly independent eigenvectors, but boom, that's one way of doing it, solving the eigenvector equation. So this is Sturm-Liouville theory in a nutshell, is that, I'm going to leave this, is that this is the function version of this. And it looks a little bit gross, so I'll write up an easier version first. So there's a thing, don't ask me what it is yet, and it acts on an unknown function x. This is the function version of that. Okay. It turns out that this is what's called a differential operator, and in practice we could have something called a weight function there. So this will be the difference in between a lot of the different sets of orthogonal functions that you guys will run into. So the full and original version, so this is L, is a differential operator. Which means it can have things that look like this inside of it, d by dx, or d by dx squared, or something like that. So it's allowed to have derivatives in it that act on the y of x. So, but this, in general, is the equivalent of this. This thing will generate orthogonal functions, so functions whose overlap is 0. So technically, the real form, the Sturm-Liouville form, is this. I'll just write it down. And again, we won't get too deep into this. I just want you to know it's there. So specifically, if you can represent a differential operator like this, so p of x is a specified function, and q, should be a q, of x is another specified function. And then w of x, that's called the weight function, is a third specified function. So this is why I didn't write it first. This is kind of like an eigenvalue or eigenvector equation for functions themselves. And it actually has the same properties. So it turns out that the solutions of y will have the same sort of properties as the eigenvectors for just this linear algebra problem. Namely, they'll span a basis, and you can use them to decompose any function you want in terms of a collection of these y's, these solutions. So we'll talk about that a little bit, but in Legendre's equation, for instance, I think is the first one we do. But what I want to do is just, because maybe this is the first time you're seeing this, talk a little bit about what differential operators are. But the idea is that in some sense, a matrix is a mapping from vectors to vectors. So in some sense, a matrix M takes 3 real numbers and gives you back 3 real numbers, right? So that's what it means to have MV equals W. Well, derivatives, if we're going to abuse this analogy of functions being like vectors, map functions to functions. So if we're going to write down the most general thing that we can write down that takes a function and spits out a function, yeah, you can multiply by 4. That'll turn a function into a function. But if we want to write down something that's really generic, we need to include derivatives, because derivatives kind of do, in a sense, what matrices do. And you can think about, when you get into maybe quantum, you'll see this, is you can actually write matrix forms of derivatives and take this as a limiting process. So, d by dx, now think about this differential operator as its own thing. Acts on a function, gives you a function, right? So it's something that's kind of like a matrix. And so we'll use notation that is evocative of that. So we'll take differential operator d is d by dx squared plus w squared. Okay? So let's just, for example, take this as our differential operator. The eigenvalue equation associated with this differential operator is something that you guys already know and love. This is the simple harmonic oscillator, right? So this is the differential operator. Which is to say, if I take dy equals lambda y, so that's kind of like the eigenvalue equation for that, and I start working through this. So that's 2. Okay, I'm going to represent this as t, just so it's a little bit more familiar. So d by dt squared, omega squared, y equals lambda y, and then, okay, so that's just omega squared, and then we can put that on the other side, and then 2 time derivatives, so d by dt y squared plus omega squared. Won't move it yet. So 2 time derivatives of y is proportional, so just call it like alpha y. And then I'll put a minus sign there formally. So what are the solutions of something that looks like this? So me just combining those 2 constants and putting a minus sign out front. These are sines and cosines. So these are solutions of the simple harmonic oscillator. And what's true about sines and cosines? Well, sines and cosines have the property that, as we talked about when we went through Fourier series, is that they comprise, in some sense, a basis. So this is what we have. So this is like the equivalent of the eigenvalue problem, is I have a differential operator. Differential operators are things like matrices. The functions that solve the eigenvalue equation for that differential operator, if they have a certain format, so that's the work that Sturm and Liouville did, is that they will actually generate for you a basis of functions. So the last part of this that we did without realizing we did it is that you guys know the solutions of the simple harmonic oscillator. So those are y of t is a cosine omega t plus phi and a sine. And now you know you can actually combine these and represent them in complex form like this, e to the I omega t plus phi. Form a basis, right? So this is the Fourier series work, that these things actually can represent any function you want in the same way that a function does. Okay, so a little bit of terminology, and then we'll just talk about specific examples of this. But what I want you guys to do is have this framework in the back of your mind so you understand why a lot of these problems kind of look alike. And especially phrasing every single one of these problems we come into, thinking about it as, look, there's just another differential operator acting on some unknown functions, and therefore they're going to have a bunch of properties. So this is the eigenfunction equation. And we could have a weight. In this case, the weight is equal to 1. The solutions are a whole bunch of y's, and they're going to have some subscript on them. So you pick a lambda is how this game is going to work. And each lambda that you pick, or is allowable by, for instance, boundary conditions, is going to correspond to a different y. So you pick lambdas. If the lambdas are OK and the thing actually has a solution, a different y is going to pop out. These y's, if this is a real Sturm-Liouville problem, are going to satisfy the following properties. So our old friend, so it could be that k's are discrete. If they're continuous, it would be the Dirac delta. If they're discrete, we would have the Kronecker delta. Right. But this is going to look familiar. So we'll go through an example in class of, I think, a Legendre function is the easiest one to deal with. And I do want to make one last comment. You will see something with a weight in it. The role of the weight is it would show up here. So when you're taking the overlap of these functions, you take overlaps with respect to the weight. But most of the things that we'll look at will have a weight equal to 1. So again, this is what we're going to do. We're going to look at a bunch of differential operators. We're going to come up with different ways of finding their solutions. But at the end of the day, what's going to happen is that all of the solutions are going to have orthogonality and completeness properties where you can represent any function you want in terms of them. And that's kind of the point in some sense, is that you're picking the basis that's most suitable to the physics problem at hand.